Hello. So now we're on our second video of um, what we're our next step in nonlinear pharmacokinetics. We're going to talk about nonlinear intrinsic clearance. And the reason we're talking about that is because this is really the source of our nonlinearity with phenytoin pharmacokinetics. So let's see if I can advance this slide. So as you recall, with hepatic clearance, we either have high extraction drugs or low extraction drugs. Remember drugs, the rusty dairy and the shiny dairy, where when drugs are very highly extracted, most of the drug is removed as it goes through the liver. The blood flow is the rate limiting step there, whereas if it's a low extraction drug where it's not quite as highly extracted as it goes through the liver, the intrinsic clearance and the fraction unbound are the determinants of the hepatic clearance. Now, which of these are going to be able to have, or which of these are going to be possibly nonlinear? Blood flow? Well, no, we can't overwhelm blood flow, right? There's not a number of receptors or a number of some place for the drug to interact with that's going to be overwhelmed. But intrinsic clearance, which is enzyme activity, there's a fixed number of enzymes, isn't there? And binding to plasma proteins obviously is also a fixed number. Both of these can be overwhelmed and have a nonlinearity. And in fact, in this case, we're going to talk about intrinsic clearance because that is what gets overwhelmed with phenytoin and is the most common source of nonlinearity clinically. Remember, intrinsic clearance is determined by Vmax over Km plus C, which is really just the Michaelis-Menten divided by concentration, which gives us intrinsic clearance. Don't worry about that. Just know that it's Vmax over Km plus C. In most cases, the concentrations that we see are much less than the Km. Therefore, the concentration falls out of the equation, and our intrinsic clearance is all about the number of enzymes available and the affinity, or the concentration, where you have half of those enzymes filled. So in this case, clearance falls out of importance and is not a determinant of intrinsic clearance. However, if that's not true, well, just as a reminder, Vmax is the maximum rate of metabolism, the capacity, or in this case, the number of enzymes is kind of how we think about it. So Vmax is possibly overwhelmed. And what about Km? Km is the concentration. We're at half of Vmax, which is our affinity, and it's a concentration, right? So in most cases, concentration falls out of the denominator, and we have a linear intrinsic clearance. Intrinsic clearance remains the same unless there's a change in Vmax or Km, which can be caused by drug and disease interactions. So in this case, as concentration increases along here, the intrinsic clearance remains constant because it won't change unless this changes, or if the concentration gets high enough where we're in this situation and the concentration has to be considered as part of the equation, and this is where we get nonlinear intrinsic clearance. So concentration increases. This should be straight. I just couldn't draw it right. Intrinsic clearance stays the same until it reaches a critical point where the concentration has to then be considered. And as concentration increases, the intrinsic clearance starts to decrease, which means the clearance will start to decrease, which means the concentration will go up even higher, and it becomes a logarithmic problem because the higher the concentration, the lower the intrinsic clearance, the lesser the clearance, the more the concentration. And you can see that it's a mounting problem, a logarithmic problem. So it's all about the relationship between these two. As long as the concentrations are much less than the Km, you'll have linear, but as soon as the concentration gets into the realm of what the Km is, then you're going to have a nonlinear situation. So which of these exhibits linear and which exhibits nonlinear? First note, this is a logarithmic scale on the y-axis, isn't it? So as time increases, if we have our log concentration, this is a linear relationship, right? We're used to the concentration falling, oopsie, in a straight line, right? From uh, if we plot it as log concentrations. But what if it isn't a straight line? No, so it's slower at being removed at these higher concentrations. So this portion is nonlinear. But then notice as the concentrations fall and get into the same range here, it becomes linear here and becomes parallel. So this is nonlinear in this section, but as the concentrations fall and the concentration can fall out of that denominator, this becomes linear, just like this drug B. So it's not the drug, it's the concentration. It's coming back to this relationship here, isn't it? So looking at these two different patients, this is natural log concentration and this is time. So we can see that again, this is a linear, this patient, FG, has a linear um, falling of the concentration here. And this patient here, you can see it's not being eliminated with time very quickly, and it's certainly not in a linear fashion. So which of these patients has, they're all at the same concentration up here, so which one of these has a higher Km? Well, this guy must have a larger Km, Fg, because the relationship between Km and concentration is what's at play here. So as long as the Km is much greater than the concentrations, it'll be linear. So patient FG has a higher Km than patient LM, doesn't it? All right, that's it. Next, we're going to talk about nonlinear binding, which also can cause nonlinearities. Okay.